In this video, we're going to look at further counting techniques. So this is really just going to let us practice the permutations and combinations from our previous video in a little bit more detail. So first problem, a box contains 5 red balls and 4 yellow balls, and 3 balls are going to be selected from the box. So first question is, how many possible selections are there? Well, in making this selection, we haven't talked about color at all. So at this point, we don't care about red versus yellow balls. We would just look at the balls and say, well, in total, there are 9 balls in this box. And what we want to do is choose 3 of them. There's no mention of order here. So we're doing an unordered selection, and that means that we're using a combination. So when we talk about combinations, we talk about how many objects we're choosing from, and then how many objects we're choosing. And then we saw in our previous video how to calculate this on our calculator. So C9, 3 gives us 84 different ways to choose 3 balls from this box of 9 balls. Now let's figure out the number of selections with 2 red and 1 yellow ball. So if we map out the choices we would be making, we would have to choose 2 red, and then we would have to choose 1 yellow. So number of ways to choose 2 red balls from the set of 5 red balls in the box, that would be C5-2. Still an unordered selection because we're not putting the balls in order. So we're using a combination for the unordered selection. The word and is going to prompt us to multiply. And then for choosing the 1 yellow, we're going to go C4-1. We have 4 yellow balls to choose from, and we're choosing 1 of them. So to calculate this, you can just calculate the individual combinations. C5-2 is 10. So we're going to go 10 times C4-1 is 4. So 10 times 4 gives us 40 possible selections there. So now let's figure out the number of selections with at least 2 red balls. Remember that the question, the big picture in the question of what we're doing here is that we are selecting 3 balls from this box. So if we're looking at a scenario where we have at least 2 red balls, that breaks that down into 2 cases. You could have 2 red, or you could have 3 red. And when we say 2 red, this situation right now, this is an incomplete description of what's happening, because remember that we're choosing 3 balls in total from this box. So to complete this description, we should really say 2 red and 1 yellow. Then we know specifically what that case looks like. So the options are either we get 2 red and 1 yellow, or we get 3 red. And we should be able to count the number of selections in each case. So the word or is going to prompt you to add, because we use the word or when we're adding up different cases. And then let's look at the first case. So number of ways to choose the 2 red and 1 yellow. That's actually what we counted in part B. So if you did it fresh, you would say, well, we're using combinations because we're doing an unordered selection. So be C5-2 for getting the red balls. The word and prompts us to multiply, and then C4-1 to get the 1 yellow ball. So that's just for that first case. And then we're going to jump over to the second case where we have 3 red balls. So 5 red balls in this box. Of those 5, we're going to choose 3 of them to be red. Okay, and then let's figure out how to do the calculation here. So what I would do is calculate the individual combination numbers on my calculator. So I'd calculate that, that, and that. And so we could figure out that we've got 10 times 4 plus another 10, and that gives us 50 possible selections. So one really important takeaway from this problem is that when you see the word and, we're going to multiply, and when we see the word or, we're going to add. So and is used when you're doing a sequence of activities, or is used when you are adding up different cases of a problem, and so you just sum the number of results from each of the cases. Next problem, we want to count how many possible full house hands there are in poker. So we talked about our standard deck of cards in our last video. Now, I would not assume that you know anything about poker. So this question contains a description of what a full house hand is. it's where you have 3 of one denomination and 2 of another denomination. So for example, you could have 3 8s and 2 queens, and that would actually be different than having this the other way around. You could also have 3 queens, 2 8s. So you can have 3 of anything, let's say 3 7s, and then 2 of something else, like 2 3s, for example. So those are all examples of full house hands. So we're going to come up with the description of the different choices we're going to have to make. And it really comes down to just thinking about this triple here, the 3 cards that have the same denomination, and then thinking about that pair. You're going to need to choose the denomination of the triple. And when we say denomination, that just means, are they 2s, are they 4s, are they queens? What is their number value? That's sometimes also called the rank, but we'll call it denomination. So we'll have to choose the denomination of the triple, and then we'll have to choose the suits for the triple. And at that point, we know exactly what that triple of cards is. So we might know, for example, okay, our denomination is 7, and then we might choose the suits and say, okay, we want the hearts, diamonds, and clubs. So now we've completely described the triple, and logically there's the word and in here because we're making a sequence of choices. So now we're going to move on to the pair. We have to do essentially the same 2 things here. We need to choose the denomination of the pair. So I'm just going to write denom for short, denomination for the pair. That means, is it a pair of 4s? Is it a pair of kings? And then we would also need to choose the suits for the pair. And once we've chosen the denomination and the suits, then we know exactly what cards are forming the pair. And therefore, this is a complete description of the cards that are in our full house hand. So now comes the counting. So each time we see this word and, that's going to prompt us to multiply. And let's think first about choosing the denomination for the triple. So remember, there are 13 denominations in the deck. The 1 is really called ace. So it's ace to 10 and then jack, queen, king. I'll just write ace to king here. There are 13 choices here. So 13 ways that we can choose the denomination of the triple. And then from there, we need to choose the suits for the triple. So remember, there are 4 suits. And what we're doing is choosing 3 of them to be the suits for our triple. This is an unordered selection. There's no mention of order here. We're just figuring out which cards we get, but we don't care in which order they're laid out on the table. So to convince yourself of this, the order of your cards on the table could actually be, queen, 8, 8, queen, queen. So order doesn't matter. We just care what 5 cards we're getting. So we're going to use a combination here of the 4 suits in the deck. We're going to choose 3 for our triple. Okay, now let's move on to the denomination for the pair. There are no longer 13 choices because we've already assigned the denomination for the triple. So there are now only 12 choices left for the denomination for the pair. That's because the triple and the pair can't have the same denomination. So you can't have like 7, 7, 7, and then 7, 7. Okay, so 12 choices for the denomination for the pair, and then let's choose suits for the pair. So of the 4 suits in the deck, we're going to make an unordered selection, and we're going to choose 2 suits for those pair cards. Okay, and then we can work out our numbers. So we've got 13 times, can use your calculator here, C43 is 4, and C42 is 6. So at the end of the day, we've got 3,744 possible full house hands in poker. So now we're going to toss a coin 4 times, and we want to figure out the number of different outcomes. Well, when we talk about tossing a coin, what we care about is whether we're getting heads or tails. So some of the options would be, you could get heads 4 times in a row. You could get something like tails, heads, heads, tails, etc. So you're tossing this coin 4 times and just looking at the sequence of heads and tails. So for the number of different outcomes, let's think about the choices we would need to make. We just figure out what's happening on the first toss, and then what's happening on the second toss, and then what's happening on the third toss, and then finally what's happening on that last toss. For each of these tosses, there are going to be 2 options, either heads or tails. And we're just going to multiply our way across here. 2 options for each toss. So we get 2 times 2 times 2 times 2, or 16 different outcomes. So part A is something that we saw back when we discussed the multiplication principle. Now we're going to make this a little more interesting, and we're going to ask, what is the number of outcomes with exactly 2 heads? So we're still tossing this coin 4 times. So the way to approach this is to choose which tosses are heads. Once you choose which tosses are heads, then the other tosses are forced to be tails. So for example, if I decide, okay, I want the first and third tosses to be heads, that completely determines what the sequence of tosses is going to be, because we're going to put heads in the first and third positions here, and we're automatically going to put tails in the other positions. So just by choosing which tosses are heads, you've completely determined your sequence of tosses there. Now what's interesting is that this is an unordered selection. And the reason is, if I say, oh, I want my third and first tosses to be heads, that's still going to give us exactly the same sequence. So third and first are heads, and the other ones are forced to be tails. So these are the same outcome. So you're just making an unordered selection of which tosses are heads, and that's going to completely determine your sequence. So that's great, because that now reduces the problem to something pretty manageable. We're just saying, okay, out of the 4 tosses, let's choose 2 to be heads. So a number of ways to do that. We're going to use a combination, because it's an unordered selection. From the 4 tosses, choose 2. And that's going to be 6 possible ways to do this. So just to convince yourself that this kind of reasoning works, as a follow-up, we could write out the 6 possibilities. So you could have heads in your first 2 positions, heads in first and third, heads in first and fourth. You could have heads in second and fourth, or second and third, or in the last 2 positions. So there are your 6 options. And really it came down to just making the choice of where the heads are going to go. So this particular problem is going to be important a little bit later on in the course, and therefore we're going to do a follow-up example and just practice this technique a little bit more. So let's say now we toss a coin 6 times, and we want to know how many outcomes have at most 2 heads. Well, when we say at most 2 heads, that means 0, 1, or 2 heads. And that word or tells us, we're going to be breaking this up into separate cases. So we could go 0 heads, or 1 head, or 2 heads. And that word or is going to prompt us to add, because we're just adding up the number of possibilities for each of the separate cases. And let's use our technique from our previous example to figure out how to do the counting in each case. So if you toss your coin 6 times and you want to figure out how many outcomes have 0 heads, really what we're doing here is choosing 0 of 6 tosses to be heads. And that's an unordered selection. So we're going to go C, 6, 0. Similarly, for the second case, we need to choose 1 of the 6 tosses to be heads. So still an unordered selection. Of the 6 tosses, choose 1 to be heads. And then of the 6 tosses, choose 2 to be heads. And what you can do now is just work out each of these numbers individually on your calculator. So C60 is 1. Hopefully that makes sense. So there's 1 sequence with no heads. That would just be tails, 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 tails. There are 6 possibilities where we have 1 head. And hopefully that also makes sense, because you're just really choosing which of the positions should have the head in it. So 6 ways to do that. And then finally, C62 is 15. So if we add those up, we get 22 different possible ways to flip this coin 6 times and end up with at most 2 heads. So let's try one more of these coin problems. Again, we're going to toss a coin 6 times, and we want to figure out how many outcomes have at least 2 heads. Okay, when we say at least 2 heads, that includes 2. That means we could have 2, 3, 4, 5, or 6 heads. So we could start to break this into cases, and we could say, okay, let's count the number of ways to have 2 heads, or a number of ways to have 3 heads, or a number of ways to have 4 heads. So you could do it this way, but it's getting a little long. So I'm going to put an unhappy face. I'm just going to say, I don't really feel like dealing with 5 separate cases here. So another way to approach this would be to say, well, let's count the total number of outcomes, and let's just subtract off the number of undesirable outcomes. So this is an indirect way to do it, but it's going to turn out to be quite a bit faster to approach it this way. So whenever you run into a problem where it's time consuming to just break it into cases and calculate it directly, then think about taking your total number of outcomes and then just subtracting off the ones that you don't want. So our total number of outcomes is just how many different outcomes can happen when you toss a coin 6 times. So that would be 2 times 2 times 2 times 2 times 2 times 2. Let's call that 2 to the 6. Okay, and then let's think about what we want to subtract off. So we want to subtract off the situation where we have 0 heads, and we also want to subtract off the situation where we have 1 head. So those are the undesirable outcomes, the ones that we don't want. So to count the number of outcomes with 0 heads, remember what we're doing is choosing 0 of the 6 tosses to be heads. So that's just a description of what we're going to do. So that's an unordered selection of the 6 tosses, choose 0 to be heads, and then to get the number of possibilities with 1 head, C6, 1. So at this point, I'm going to erase the first thing that we tried because we decided that was not very efficient. Okay, and let's see if we can do our calculation quickly. So we've got 2 to the 6 minus C60 is 1. So we subtract that off, and we also need to subtract off C61, which is 6. So altogether, got our final answer coming up here. 64 minus 7 gives us 57 different possible outcomes. So here's a completely new type of problem. Imagine that we're looking at some city blocks and we're trying to go from point A to point B. We want to figure out the number of shortest routes from A to B. So when we say a shortest route, it means we're allowed to travel right and down to get from A to B. We can do that in any order that we want. So we could say go right and then go 2 blocks down and then go right for a bit and then go down and then go right. But what we're not allowed to do is backtrack. So we aren't allowed to do something like, go down and then later come back up. So that would not be a shortest route. So let's see if we can come up with a better description of what a shortest route is. Well, we're going to have to travel down 4 times over the course of our route. And we're also going to need to travel right 5 times over the course of the route. So instead of saying down and right, let's actually call it south and east. And let's point out that we're going to need to go 5 blocks east at some point during the route, and we're going to need to go 4 blocks south at some point during the route. So 4 blocks south and 5 blocks east in some order. So for example, what you can do is just write out any sequence of 4 S's and 5 E's, and that's going to define your route. So if we try to describe the route that we actually drew in blue in our picture here, it was east and then south-south. So that represents going south for 2 blocks. Then we went east-east-east, south-south, east. Each sequence like that is going to define a different shortest route for us. Okay, so that's interesting because now this starts to look a lot like the coin problem. I mean, with coins, we were talking about T and H for heads and tails. Now we're talking about E and S for east and south, but it's essentially the same problem. So when we ask how many of these shortest routes are there, we're really asking how many ways to choose 4 of 9 positions to be south. And then we'll say E is forced in the other positions. So number of ways to do that. It's an unordered selection, just like with the coin problems. Because if you say, okay, I want my second, third, 7th and 8th positions to be south, you get that. But if you say those positions in another order, you still get the same sequence. So if I say, okay, I want 7th, 8th, 3rd, and 2nd to be S, you still end up with that exact same sequence. So it's an unordered selection. You're just figuring out which positions you want to be south. So of the 9 positions, choose 4 of them. And you can do that on your calculator. It's 126. So that might be one person's approach. And then another person might say, oh, but I don't want to think about south. I want to think about east. So alternatively, you could choose 5 of 9 positions to be east. And if you approach it that way, then south, so the other letter, is going to be forced into the other positions. So once you've decided where east is going, there's no freedom for south. So there's nothing to choose in terms of south. And if you approach the problem this way, then your answer would be, well, again, an unordered selection of the 9 positions, choose 5 to be east. So if you try that on your calculator, that also comes out to 126. So that's another way of arriving at the correct answer. So bottom line here is that you only need to think about south and then east is forced, or vice versa. And along the way, we figured out kind of a cool fact about these combinations. So we figured out that C94 was the same thing as C95. If you look at the second numbers here, they add up to 9. So if you were to write this more generally, you're taking the number of combinations from a set of n objects and you're choosing r of them. That's going to be the same thing as if you're looking at the number of combinations from a set of n objects where you're choosing n minus r of them. So as long as your second numbers here add up to your first number, then your number of combinations is going to be equal. So this is not something that you need to memorize. It's just something you might notice as you go through these counting problems. So I'll just call this an aside. This comes up often when 2 people are solving the same problem. So another example of that would be if you did, say, C12, 5, that's going to be the same thing as C12, 7. So you can choose 5 of 12 objects to grab, or you can choose 7 of 12 objects to leave behind. And either way, you are making the same choice of how to select the objects. So now we're going to modify this problem. So same kind of setting where you have these 2 locations, A and B. If you look at location B, it's 4 blocks south and 5 blocks east of location A. And we want to figure out the number of shortest routes from A to B that don't go south for 2 consecutive blocks. So for example, you could have something like south, east, east, southeast, southeast, southeast. That would work. So we've gone 5 blocks east in total, and we've also gone 4 blocks south in total, and we've just made it so that we don't have 2 S's side by side. So we never walk south twice in a row. So the problem then is going to come down to how can we make sure that the S's are separated when we write out this sequence? Well, the way we could do that is we could start with just writing out 5 E's. And these 5 E's actually create 6 different spaces where we could put in some S's. So think of these E's as spacers. They're making sure that the S's stay spaced out. And then we can choose 4 of these 6 positions to be S. And however we make that choice, we are going to have a route that goes south 4 times, that goes east 5 times, and it also makes sure that the S's stay spaced out. So number of ways to do this. Well, it's an unordered selection. From 6 positions, choose 4 to be south. What we can do is just illustrate where those S's are going to go. So that then produces your shortest route, which would look like SE, E, SE, SE, SE. So you can grab your calculator then. C64 is 15. And that's our number of shortest routes from A to B that don't go south for 2 consecutive blocks. So now for a completely different problem. In how many 4-digit numbers are the digits strictly decreasing from left to right? So an example would be 9730 or something like 8421. So we can use the digits 0 through 9. We cannot repeat digits because we need to make sure that the digits are getting smaller as we go from left to right. And we just need to make sure that they're in the correct order so that they are decreasing. So 6, 4, 3, 1, for example, would be another desirable outcome. So if we think about what choices we need to make here, it's really just about choosing the 4 digits that we're going to use. So let's choose 4 of 10 digits. Remember, it's 10 digits because we're using 0 through 9. And then from there, the order of the digits is forced because there's going to be only one way to write out those digits in decreasing order. So I'm just going to write ordering is forced. So number of ways to choose 4 digits from 10. That's an unordered selection. You're just deciding which digits to use. So that would be C10-4. And then we're going to multiply. If something's forced, that means there's only one way to do it. So you can grab your calculator. C10-4 is 210. So just to illustrate our process here, if we choose 4 of 10 digits and we say, okay, our choice is 3, 7, 2, and 6, for example. These are all jumbled up. They're not in order. There's only one way to form a decreasing sequence from these numbers. You would be forced to have 7, 6, 3, 2. So that's why there's no choice for the ordering. So here's our very last problem for this video. 5 students sit in a row. How many arrangements are there so that Al is to the right of Bob? Okay, so we could draw a picture here. So here are our 5 students. If we choose 2 positions for Al and Bob, let's say these 2 positions, within those 2 positions, we know how Al and Bob will be seated. So it's the other way around. Al has to be to the right of Bob. So Al would have to be here. Bob would have to be there. So I guess Al is being very particular today, and he just needs to be to the right of Bob for some reason. So let's think about the choices we're going to have to make. Since there is a restriction on Al and Bob, it would be good to choose the 2 seats for Al and Bob first. That'll be our first choice. And then we can think about how to order Al and Bob in those 2 seats. And then we still have 3 other students who need to sit somewhere. And because these seats are in a row, they are going to be ordered within those seats. So we could just say order the other 3 students. See, we don't need to actually choose seats for the other 3 students because we know the other 3 students will be forced into the other 3 seats. It's just a matter of what order are they going to be in those other 3 seats. Okay, so let's think about how many ways to do this. Choosing 2 seats for Al and Bob. Well, of the 5 seats, choose 2 to be for Al and Bob. Right now, that's an unordered selection. We're just picking which 2 seats we want. And then we're going to multiply. Let's think about how many ways to order Al and Bob in those 2 seats. There's only one, because Al is just being picky today and he's saying he has to be to the right of Bob. So there's just one way to make that happen. Okay, and now that we've taken care of Bob and Al, we need to think about the other 3 students filling into the other 3 open seats. So that is going to be an ordered selection of 3 objects chosen from 3 objects. So there are a few different ways to describe that. You could say 3 times 2 times 1. If you like the multiplication principle, you could call that 3 factorial using the factorial notation that we saw in our previous video. Or you could consider that to be a permutation. It's an ordered selection of 3 objects chosen from 3 objects, because you're just picking all 3 students in order to fill into those 3 remaining seats. So however you choose to describe that number, it is 6. 6 ways to fill in the other 3 students. So final answer then, C52 is 10. So we got 10 choices for the 2 seats that Al and Bob could be sitting in, only one way to put them into those 2 seats, and then 6 ways to arrange the other 3 students. So 60 ways in total. So that's our video on further counting techniques. Hopefully we are gradually getting more comfortable with combinations and permutations, and we'll continue to practice these ideas as we get into probability in our next chapter. Thanks for watching.